Okay, we'll take a few minutes to go over the Unit 5 physics homework for thermodynamics. We're doing problems 5 through 12 today. So we'll start with problem number 5. Problem 5 is a conservation of energy problem. So we're going to start with a 2 kilogram block, and we're going to have it slide down a ramp. And because there is going to be friction, we're going to have some increase in internal energy. But we're going to use conservation of energy to solve this particular problem. So we start off with our energy equation, 1/2 mv squared plus mgh plus the initial internal energy is going to equal the final 1/2 mv squared plus mgh plus the final internal energy. So knowing what we know, we got first of all, the first one is not going to be moving, it's starting on a block. So we're just going to have potential energy, so mg times the h, which is 5 meters, plus the internal energy. And that's going to equal the 1/2 mv squared final, because it is moving at the bottom, and it's lost its potential, so that part goes away, plus the final energy. Now we ask for the change in internal energy, which is U final minus U initial. So when we solve for that, we're going to get, by manipulating algebraically, 34 joules. Okay, next problem. Another conservation of energy problem. In this problem, we have a bullet moving at 300 meters per second. It's going to hit a block and come to stop. So you can imagine it starts off with lots of kinetic energy, and then it ends up converting all of that into internal energy because it comes to a stop. So from our equation, we can eliminate the mgh on both sides. There's no potential energy in this problem. We do have to be careful about thinking about the mass, because it was 50 grams, which is 0.050 kilograms. Like, you got to keep your SI units straight. So we have 1/2 mv squared plus internal energy initially, and then afterwards, all of the energy is converted to internal energy. There's no 1/2 mv squared, there's no mgh, so you just get U sub f. So the final, or the change in energy then is UF minus UI again, which is going to give us, in this case, 2250 joules, which will round off to 2300 joules when we want to talk about sig figs. Okay, next one, number 7, also conservation of energy problem. 1/2 mv squared plus 1 mgh. In this problem, we have a lead ball being dropped from the top of a building, and when it falls, it's going to come to a stop, so it'll lose its kinetic energy and potential energy, and all of the energy will be transferred into internal energy. So let's go ahead and calculate it. Initially, we don't have any kinetic energy, so we can cancel that one. It's all going to be potential, mgh, plus its internal energy, ui. When it hits the ground, all that energy is going to be converted to internal, plus whatever the internal it started with. So I say 1500 joules plus whatever it started with. So now we can see that you have I on both sides, so we can subtract that from both sides, and that will go away. And then we just solve for h, and we get h is 1500 divided by 3 times 9.8, which is 51 meters. All right, number 8, now we're getting into calorimetry problems. We have copper, and we want to increase its temperature 50 degrees Celsius, and the question is how much heat is required to do that. So we're going to use MCAT, or MC delta P. I'm sorry, MC delta T. MC sub P delta T. For copper, C sub P is 387, so we go 2 kilograms times 387, and the units are joules per kilogram degrees Celsius. You got to really be careful about your C sub P's, especially if you're getting them off the internet, to make sure the units are kilograms and your mass is kilograms. In other words, keep those masses consistent. Either have your C sub P be in joules per gram degrees Celsius, and then have your mass be in grams, or have them both be in kilograms. So you got to be really careful about those units. Okay, so we end up with 39 joules when we're kilojoules. Sorry, when we're talking about significant figures. Okay, number 9. Number 9 is another calorimetry problem. In this case, we have a solid. We don't know what its value for C sub P is, but we do know it starts off at 90 degrees, so that's going to be the hot temperature, and it's going to cool off to 25 degrees. And we're going to dunk it in water, and we know we have 0.25 kilograms of water. We know it's going to start at 20 degrees Celsius, but when we put the hot metal into it, it's going to increase to 25. So I like to keep track of my temperatures. I call them T hot and T cold. And when I set up my equations, I don't have to worry about the signs, like where's the negative sign. I just remember it's always hot minus cold, because whatever one gains, the other one's going to lose. And if you just keep hot minus cold, all the numbers work out nicely. So NC sub P times T hot minus T cold of the unknown metal is going to equal MC sub P of the water times its hot minus cold. So now we plug in the values, and we're going to solve for C sub P. So we got 0.5 kilograms of the metal times C sub P, which we're looking for, times 90 minus 25, because the thing starts hot and cools off. And then the water is going to be 0.25 kilograms times 4186. That's the C sub P for water. And then the hot is going to warm up to 25 degrees, so we say 25 minus 20 is your T sub C. So now I solve for C sub P, and I'm going to get 161 joules per kilogram degrees Celsius. Okay, number 10. Another calorimetry problem. In this case, though, we know the C sub P values, we know the metals. The question is, what temperature are they going to end up at when you mix them? And the idea is the heat that one loses has got to equal the heat the other one gains. So I set it up and I say m C sub P delta T for the hot metal, and then m C sub P for the water. Now the key here is the way you set up the equation, so that you know that when it's hot minus cold for the metal, right here, the hot minus cold for the metal, it starts at 80 and it drops down to some final temperature. But then for the water, it starts at 20, that's the T cold, but it warms up to some temperature, so hot minus cold is going to be TF minus 20. So that's the trickiest part of this problem. Well, I guess that's the first trickiest part. The second trickiest part is just to do the algebra, is to multiply and then distribute, so that you get a rather complicated algebraic expression. So here we go. I get 480 minus 256 times the final temperature equals 6279 times the final temperature minus 125, 580. And now I'm just going to be careful in keeping track and combining my TFs on one side and my heat values on the other. And when I finally solve, I get TF is 22.4 degrees Celsius. We're only entitled to 2 sig figs, so I'm going to round that to 22 degrees Celsius. Okay, number 11 I'm going to skip for now because I'm going to do it on a separate page. I'll do number 12. Number 12 is a fusion problem. In other words, you're going to be taking ice and you're melting it. And how much energy, if you have a certain amount of energy, how much ice is going to get melted? Well, 5 kilojoules is 5,000 joules is going to equal the mass times the latent heat of fusion for water. So you say the mass, when you solve, is going to be whatever the energy is divided by latent heat of fusion. So 5,000 divided by 3.33 times 10 to the 5th joules per kilogram. So 0.015 kilograms is your final answer. That's how much ice is going to melt to give off that much heat. Okay, number 11. Rather complicated. What we're going to do is take 2 kilograms of water that's at 150 degrees Celsius, and we're going to drop it to 50 degrees Celsius. Minus 50. And then we're going to graph how much energy or heat we're pulling away in order to cause that change. Now this is a tedious calculation, but it's not a difficult calculation. We just have to be methodical and think about each phase or stage of this energy change or temperature change. So we're going to go from 150 to 100 degrees Celsius. So the first step is going to be an MC sub P delta T situation. We have hot steam. It's at 150 Celsius. We want to get down to 100 degrees Celsius. So Q is MC sub P delta T. Now we got to know that we got 2 kilograms, 0.2 kilograms of water. And we know that the C sub P for steam, you have to look it up, it's different for water, is 2010 joules per kilogram degrees Celsius. So you got to be careful and make sure you get the right C sub P value. Then we're going to go change in temperature. Now the final temperature is going to be 100 and the initial is going to be 150. So final minus initial, and that's going to give you a negative value. So we get a total of negative 20,100 joules. What does that mean? Well, we're taking heat away in order to cool this thing off. So you have to remove the heat. Okay, so that's the first value. Now I'm not going to do my graph until I have all of my numbers and I get a sense of how big my graph has to be. So I'm just going to collect all these values and then we'll graph it at the end. Okay, so the next step, now we've got 100 degree steam. We want to cool it, we want to condense it, turn it from steam into liquid water. And so that's the next phase. So we're going to condense. In that case, we're going to use the latent heat of vaporization. So M times the latent heat of vaporization. Remember, there's no temperature change when we're condensing. So 0.2 kilograms times 2.86 times 10 to the 6 joules per kilogram degree Celsius, 452,000 joules. So that's a huge chunk of energy. As you see, most of the energy is going to go in changing the steam into liquid. Okay, next thing, we're going to have 100 degrees Celsius water, and we want to change it to 100 degrees Celsius. So now we are going to have a temperature change. This is another MCAT, MC delta P. I keep saying that, MC delta T. In this case, C sub P is for liquid water, 4186. And the change in temperature is 0 minus 100. And so now we're going to get it down to 0 degrees. Okay, so 84,000-ish joules to do that. Now we have liquid water at 0 degrees Celsius. We want to change it into ice. So that's going to be the latent heat of fusion. So the mass, 0.2 kilograms, times the latent heat of fusion for ice, which we can look up in our book, 3.33 times 10 to the 5th joules per kilogram, for a total of 66,600 joules. That's going to be negative 2. And then finally, we have ice, and we want to cool it off to 50 degrees Celsius, or minus 50 degrees. So now we have MC sub P delta T. C sub P this time is for ice, not liquid. And the final is negative 50 minus the initial 0 for negative 20,900 joules. Okay, so when we add all these up, it looks like we're going to get in the neighborhood of 600 and something thousand joules. So that's how we want to set up our graph. Okay, so let's start by graphing what's going to happen for the first phase. Okay, oops, I went too fast. First phase, remember you're taking away 20,000 joules to go from 150 degrees to 100 degrees. So I'm going to label down here. That negative 20,000 joules. Okay, I'm not putting negatives, I'm just keeping it positive. This is the heat removed. So 20,000 joules to go from 150 to 100. That's going to be my first tick. And then the next one is going to be 450,000. So I add that to 20 for a total of 472,000. And so 472 is where my next data point is going to be. And that's, remember, and notice the temperature stays at 100 degrees because we don't change temperature when we're changing phase, going from steam to liquid. Now we have 100 degrees Celsius liquid. We want to cool it off. So it's an MC delta T. So that's got 83,720 joules. So let's add 84 to that 472, and we get about 556 kilojoules. And then we're going to freeze it. And that's going to cost us another 6,600 joules, 66,000, sorry. And then we're going to cool it off. And so we just step through adding up the values as we go to create a nice, lovely graph. And then each little part of the graph represents one chunk of the process in chilling this water. So it starts at high temperature steam, then we cool it off. That's phase 1. Phase 2, we condense it. Takes a lot of energy to condense it. And then we have 100 degree liquid. Then we're going to cool that. That's phase 3. We pull out heat to do that. And then phase 4 is when we're going to freeze it. That takes a good chunk of energy too. And then phase 5, obviously this thing is not perfectly to scale, but you get the idea. Phase 5, we're going to pull away 21,000 joules in order to bring it down to negative 50 Celsius. And that concludes our homework.